Okay, so it's almost 6:05. Maybe we can start slowly, others will also join. So, good evening, everyone. Um, I am Desha Devi, a PMRF Fellow from IIT Gandhinagar. I welcome you all to week 3 of problem solving session for NLOG Circuits course. Before starting, I would like to confirm if I am audible clearly. Am I audible clearly? Okay. So, in case you have any doubts, please unmute yourself and ask it immediately, okay? Don't wait till the end of the session. Alright. So, before starting with the problems today, uh, let's delve a little bit into body plots and transfer functions. Alright. So, last time also we discussed a little that transfer functions are basically V out versus V in when we write it in terms of J omega or S, right? So it has a numerator and a denominator. The roots of numerators are called zeros, and the roots for denominators we call them poles. Okay, so when you plot frequency versus gain, ideally in dBs, if you plot this graph, like you take experimental values and plot it, we call it frequency response, right? But when you theoretically analyze your transfer functions, you can again plot this frequency response with um, some approximations. And that particular curve, which is theoretically analyzed and which has few approximations, we call that curve a Bode plot. Okay. So Bode plot is nothing but the frequency response. The only thing is frequency response is the actual response, whereas Bode plot has few approximations. Alright. So there are few rules that we follow to plot this Bode plot. Okay. Now, rules for plotting Bode plots. First, when we encounter a zero in the frequency response, the slope of the curve increases by 20 dB per decade. So for now, just note down these points. I'll explain it to you. We'll do some examples to get these points clear. Okay. So similarly, when we encounter a zero, encounter a pole, the slope of the curve decreases by 20 dB per decade. So this means basically your slope changes by plus 20 dB per decade, and in here we have slope change of 20 dB minus 20 dB per decade. In y-axis, we have gain. All right. And when you talk about frequency responses or Bode plots, these are there are two types of plots. One is magnitude plot, which is gain versus frequency, right? Another is phase plot, which is phase versus frequency, right? Uh, Frequency plot is something, sorry, magnitude plot is something which is um, considered most of the time and most frequently. However, in few cases, we also look into phase plot because we can deduce certain information from phase plots as well. So that's why both magnitude plot as well as phase plots are equally important. It's just that magnitude plots are more common um, for analysis compared to phase plots. But both magnitude and phase plots are available. All right. So in y-axis, we have gain, which is presented in dBs, or phase in degrees or radians, whatever you feel like. And in x-axis, we plot frequencies in decades. Decades means in multiples of 10. Okay. So the idea is in this frequency plot or Bode plot, we want to encapsulate the behavior throughout the frequency ranges. And why we plot the y-axis and dBs, the reason being dB means log axis, right? So again, log axis basically helps us to incorporate uh, very small values as well as very larger values in a very small range. So that is the idea we go for these log accesses. Okay. So yeah, there are basic these three formulas that we consider, and yeah, with this, maybe we can take one example to understand this behavior. Okay. So let's say I have this transfer function. Right? So let's consider this example. In this example, first of all, how many zeros are there and how many poles are there? Yes, how many zeros do we have and how many poles do we have? Yes, two zeros. Please unmute yourself and answer. Okay. So we have two zeros. And what are those zeros? Like the values. The frequency values are at -10 and minus 10,000. What is the unit of this frequency? Like -10, -1,000. What is the unit? Is it hertz, kilohertz, radians? What is it? Okay. So whenever you have s equal to minus 10, this is basically in radians. Okay. If you want to find the frequency in hertz, basically you need to convert it to omega is 2 pi f, right? So f is omega upon 2 pi. So your f will be 2 pi hertz. Okay. Please keep this in mind because sometimes because of these conversions, the values definitely change. Okay. And similarly, as we have two zeros, there are three poles, and the values of poles are at 1, 100, and 10K. Right? Now, there is a term called DC gain. So DC gain basically means low frequency gain. DC gain, or sometimes it is also referred to as low frequency gain. So the idea is when your frequency is very, very small, what is the gain of your system? So ideally, how do we calculate this DC gain or low frequency gain? We substitute is equal to 0. Okay. So when you substitute the transfer function with s equal to 0, what will you get? 100 into 10 into 1 0, 1 into 100 into 10K. So what is the DC gain that we are obtaining for our transfer function over here? So DC gain comes out to be 1. But this DC gain is in volt by volt, right? So here we need to convert this DC gain into dBs, decibels, let's say 20 log, which is 0 dBs, right? So 0 dB is the uh, DC gain or low frequency gain of our given transfer function, right? So now let's try to plot our transfer function across frequencies, which is basically the Bode plot, right? So here we will write gain in dBs, and here we have frequency and writing in radians. Okay, so as I mentioned, the frequency axis is changing by decades, and I have my first pole at 1. So let's start with from 1. Okay, so 1, 10, 1000, 20K, 100K, 1 meg. These are the frequencies. And here, let's say I have 0 dBs. So Okay. So here we have two zeros at minus 10 and 1000. So these frequencies are all in negative. So basically, in Bode plot, we don't consider the sign of the frequencies. Whatever frequency you get, you generally plot them. And most of the times, we want to have negative poles and negative zeros due to stability perspective. So yeah, that is the idea. So here we had a 0 at minus 10 and at minus 1000. So I'm denoting 0 by the small circles and I'll denote the poles by a cross. Okay, so poles are at 100 and 10,000. So we have one pole at 1, another pole at 100, and a pole at 10,000. Okay, so since this particular graph has a decade scale, so let's consider that this graph is starting from point 0.1 radians frequency. Okay, just as we need to start somewhere, right? So, what is the purpose of the DC gain that we calculated right now? So, the DC gain is the gain at which your curve starts. Okay, so whatever DC gain you get, you will start your curve from that particular value. So here we got 0 dBs. So you start your curve from 0 dBs and you'll draw a straight line. So this particular 0 dBs is maintained until you encounter a pole or a zero. Okay, so now you encounter your first pole at 1, right? So when you encounter a first pole at 1, so your slope changes by minus 20 dBs per decade. Correct? So your slope changes by minus 20 dBs per decade. So until now your slope was 0 dBs per decade. Now your slope changes by minus 20 dBs per decade. What does that mean? That uh, when you transit by a when you transit by a decade, your gain has reduced by 20 dBs. Okay, so you have transited by a decade in frequency, and your gain has dropped down by 20 dBs. So that is the idea, 20 dBs per decade. Now, similarly, if it was a zero, you would increase your gain by 20 dBs per decade. Okay, so now at 10, again, you observe that there is a 0. So till now, your slope is minus 20 dBs per decade. You encounter a 0, which introduces a slope of plus 20 dBs per decade, right? So what is the resultant slope? So minus 20 dB per decade plus 20 dB per decade. So the slope becomes 0 dBs per decade. So now from 10 to 100, your slope will become 0 dB per decade. Is this clear to everyone? Why the slope becomes 20 dB per decade at this point? Is this clear to everyone?
Yes.
Okay. So now again see at 100 radians, you again encounter a pole. So when there is a
Can you
pole,
explain that
you're sorry.
minus 20 dB per decade? How we get that?
So this is basically the rules. These are basically the rules of Bode plot. From Bode plot rules, we know that whenever we encounter a single pole, the slope will reduce by 20 dB per decade. So that means the slope will be minus 20 dBs per decade. We'll introduce minus 20 dBs per decade as the slope. When we encounter 1 0, a single zero, the slope becomes
Okay.
plus 20 dB per decade. Yes. And it also changes by number of poles and number of zeros. Like, so I can write it here as plus 20 in dBs per decade for n zeros. So it's like when you have multiple poles or multiple zeros at the same frequency, you multiply your slope values by that many numbers. Okay. Okay. So now again see at 100 radians, we encounter a pole. So as we encounter a pole, we need to introduce a slope of minus 20 dB per decade. Earlier, the graph had a slope of 0 dB per decade. We are introducing a slope of minus 20 dB per decade. So the resultant slope of the graph would be minus 20 dB per decade. And now, what is the value of, in the y-axis? What will be this value? Yes, what is this value? The slope is again minus 20 dB per decade, right?
So minus 40 dB.
Yes, so it will become minus 40 degrees. Okay, so now again see at 1000 we have a 0. So since we have one 0, our resultant slope will again become 0 dBs per decade, right? It becomes 0 dBs per decade because plus minus 0. And again, you encounter another pole. So when you encounter another pole, so this the new slope that we will observe will be again minus 20 dBs per decade. Here we'll again observe minus 20 dBs per decade, and here we will see minus 60 dBs, right? So now let's do some experiments, change few things and see how our graph changes. Let's say at 1000, okay, at 1000 radians, if I had two zeros, so I'm drawing this new zeros with green color, right? So if I had two zeros at 1000, how will my graph change from 1000? So before 1000, everything will remain same, right? As nothing is changing over there. So after 1000, how will my graph change? So see, at 1000, yes, the graph will move up, and let's observe how. So at this point, since you are encountering two zeros, so one zero introduces plus 20 dB slope. Two zeros will introduce plus 40 dB slope, plus 40 dB per decade slope. And your earlier the graph was moving with a slope of minus 20 dB per decade. So the resultant slope of the system becomes plus 20 dB per decade, right? So we will again move to the same value with the slope being plus 20 dB per decade. Now when it encounters a pole at 10,000, the slope becomes 0 dB per decade, right? So this is the idea. And you can see how the shape of your curve and along with it the behaviors will change as you are changing the poles and zeros positions, right? Uh, Likewise, say in the same example, I'm not changing anything. Just the only thing that I'll change is DC gain, and let's see how things change. Okay. Here's example two. This is example one. So, okay. So let's increase our gain by how much? How much do you want me to increase the gain? Maybe let's increase the gain by 100. Okay. So now how much will you get the DC gain in this particular case when s equal to 0? Since you have increased it by 100, so definitely your DC gain would be 100. But this isn't volt by volt. Again, you have to convert this to dBs. So when you convert 100 to dBs, you will get 40 dBs, right? So now your graph will start from 40 dBs. Okay. So again, we'll follow the same procedure. Let me change the color. Okay. So here, since 0 dB is your DC gain, you will start your curve and you encounter your first pole at 1. So what is the slope of the curve? The slope of curve will change from by minus 20 dBs per decade, right? So the slope becomes minus 20 dB per decade. And right now we are at 20 dBs. Correct? Then you are encountering a 0. So the resultant slope will become how much? 0 dBs per decade, right? Because minus 20 plus 20 cancels each other. Again, there is a pole at 100, so the slope changes by minus 20. So here again, you'll have minus 20 dB per decade. Okay, so what is the value over here? This is 0 dBs, right? And again, you observe a 0, so it will be a straight line. Here you will see it is 0 dBs per decade. Then again, you observe a pole, so your curve will continue with a slope of minus 20 dBs per decade. And here we'll get two values of minus 20 dBs, and let's say here we are getting 40 dBs. Now, there is something interesting about this particular plot that I want to highlight basically. The 0 dB gain line. Okay. So let's understand one thing. When we say gain is 0 dBs, gain being 0 dB means 1 volt by volt, right? So 1 volt by volt gain, what does that mean? That is V out equal to V in. Now, if we go below this, your output is actually smaller than your input, correct? So whatever gain you are getting above 0 dB, that is positive dBs, those are actual gains. But when your gain starts becoming negative in dBs, you are actually getting attenuation, right? And the frequency at which your frequency response cuts the 0 dB point and your like gain starts moving below 0, we call that gain crossover frequency. So in our case, this is gain crossover frequency. Okay, so the point where your gain crosses 0 dB and it goes negative, that particular frequency we call it gain crossover frequency. Okay, and last time we discussed stability, right? And we said that it is calculated based on phase margin. Sorry. Okay. Do you have any doubts? Anybody? All right. So we were talking about gain crossover frequency. So this particular gain crossover frequency is important. So whenever we are talking about stability, we check the stability at gain crossover frequency.
हेलो मैम, पेपर
Right?
कब होगा?
Sorry.
मैम एग्जाम कब होगा इसका?
एग्जाम का नोटिस आ गया है। उसका डेट डिस्क्लोज नहीं हुआ है क्या? नहीं हुआ होगा तो कुछ दिन में डिस्क्लोज हो जाएगा।
जी मैम।
अप्रैल में होगा एग्जाम।
जी मैम।
ओके।
थैंक यू मैम।
ओके, आप म्यूट कर लीजिए प्लीज। या थैंक यू। Okay, so the idea is this particular frequency is gain crossover frequency. And when we are calculating phase margin for stability, we calculate phase margin at crossover, gain crossover frequency. That's why this particular frequency is very important. And we generally have, like, we keep this in mind, this particular frequency in mind, as this uh, directly or indirectly, it basically relates to the stability of the system. That's why this is important. So you can also keep this term in mind. So this is called gain crossover frequency. Okay. So yeah, like this. So here you can see, right, how the curve changes and how things change. And the basic difference that you observe from an actual frequency response to that of Bode plot is at the poles and zeros value, the exact values. So what actually happens is when you encounter a pole, your gain actually reduces by 3 dBs. So it becomes minus 3 dBs. Okay. So here, let's say you are seeing 40 dBs, right? 40 dBs at 1 radiance frequency. But in actual frequency response, the frequency value, so the gain value that you will observe at 1 radians would be 40 minus 3, that is 37 dBs. So which will be somewhat here. And your curve will slowly change, right? You will see this transition. So this corresponds to actual frequency response, and this value is minus 3 dBs. Or I can say this is 3 dBs, right? So that difference is 3 dBs. It reduces by 3 dBs for a pole value, and it increases by 3 dBs for a zero value. Okay, so that is the only difference that you observe in actual frequency response to that of Bode plot. So it is very closely related. That's why most of the times we go for Bode magnitude plots. But whenever phase plots are considered, like Bode phase plots, most of the time we go for actual phase plots rather than the, um, I would say, rather than an approximate one, because we'll get a better understanding from there. So, yeah, that is the idea. So, all of you, did you understand the concept of Bode plots? Like how to plot Bode plots? So, if a transfer function is given to you, can you plot the Bode plots now? So, the gain values can change. Gain values need not to be 40, 20, 0. Only these. It can be 10, it can be 15, it can be 13 also. But the things will change. We'll try to change them in 20 dB per decades or 20 MDB per decades kind of pattern. So you will observe that. So if my plot was starting from say 38, so in this particular case, it was starting from 38. The next step that I did here, which is 20 dBs, instead of 20 dBs, I would see 18 dBs. Okay, so that can still happen. And also in y-axis, we make sure that our scale is divided in the powers of 10. Yeah, please, if you have any doubt, unmute yourself and ask.
Ma'am, in assignment 3, there was a question that it wasn't mentioned slope of the body plots. Then how to
Sorry.
solve them? Slope of the body plots was not given in that.
Something must have been given, right? So slopes are, see, if you have a single pole, then the slope will change by minus 20 dB per decade. If you have a zero, the slope will change by plus 20 dB per decade. That is fixed. Okay. So any Bode plot which has been plotted uses this particular condition. Now, for suppose you only see a plot. So let's take an example. Um, so say, for example, You have this Bode plot, right? This is gain in dBs. This is frequency. It's in radians. And okay, for now, let this be the case. 60 units. So 10, 100, 1000, 10K. Okay. Right. Now, in this example, first of all, you all, this graph is clearly visible to you people, right? Now, tell me one by one, what is the DC gain of this particular system that we are observing right now? What is the DC gain?
60.
60 dBs. Yes. Now, you have to tell me about the poles and zeros. Okay? Let's understand. First of all, at 10 radians, is there a pole present or a zero?
Pole.
Pole. And how many poles are present?
2.
How to? Why to?
10 and 100 there are 2 poles. Slope was
No, no.
decaying.
So I'm
At
asking
100 it
at
was
10 only. I'm asking at 10 only. How many poles are present? So we'll go one by one. Okay? So how many poles are present at 10?
1.
Only one pole, right? Because the slope is minus 20 dBs per decade. Correct? Now what about 100? At 100, how many, is it a pole or a zero at 100?
pole, ma'am. 2
Two
It's a
poles.
poles.
pole. Two poles. Why two?
40 minus 0.
Okay, so it's
Maybe
40
40 dB.
minus. Okay,
This is
so
minus 40 dB per decade.
here it is minus 40 dB per decade. I agree with you. But earlier, the curve already had a slope of minus 20 dB per decade, right? So the resultant improvement or change in slope is how much? Minus 20 dB per decade only, right? The change in slope
Right.
is only of minus 20 dB per decade, right? So
Yes, ma'am.
there is only one pole present at 100, correct?
Right.
Right. So we have one pole at 100. Now, if you observe at 1000, so what is the situation at 1000? First of all, what is the transition in slope? So the transition in slope is plus 40 dB per decade, correct?
So 2 zeros.
So if transition is plus 40 dB per decade, that means you have two poles, sorry, two zeros at same 1000. So you have two zeros at 1000, correct? Now, if I ask you to write the transfer function for this particular system, can you write the transfer function?
Yes, ma'am.
How do we start? So be mindful that my DC gain should meet at the end. The value of DC gain should meet at the end. So for that, how I will start writing my transfer function is, I'll write my poles and zeros. So my pole is at 10, so that is S plus 10. Then I have a pole at 100, this is S plus 100. And I have two zeros at 1000, right? So it is S plus 1000 whole square. correct? Now, for now, if I analyze putting s equal to 0, what is the scenario? I have 1000 into 1000 by 10 into 100, which is basically 1000, right? So now, in this particular case, if I see at s equal to 0, I'm getting 1000 as my gain. And if I convert this 1000 to dBs, it will become 60 dBs. And earlier, my requirement was also 60 dBs. So I need not to add any factor over here. Okay?
Yes, ma'am.
But say if I would have got in place of this, if I would have got 100 in place of this, right? Then if I convert this, it will become 40 dBs per decade, like 40 dBs, right? And to get 60 dB, 60 dB equals to 1000 word by word. So I need to add a factor of 100 over here. Getting my point? So this is how you construct a transfer function looking at Bode plots.
From minus 20 dB per decade to minus 40, right?
Sorry,
Minus 20 dB per decade to minus 40 dB per decade. Only one pole. 100.
yes, only one pole at 100.
Oh,
Because we know that one pole introduces a slope change of 20 dB per decades only. And since the slope change, we should always observe the change in slope. Rather than exact value of slope, we should always observe the transition in slope or the change in slope.
then it should continue.
Sorry?
It should continue in minus 20 dB per decade if it is one pole.
Yeah, so that's what I did. No, at 100, we only have one pole. Now, from minus 40 dB
It
to
is
0,
minus 40.
sorry. So,
But it's minus 40.
yeah, it is minus 40 dB per decade minus 20 dB per decade equal to minus 20 dB per decade, right? And minus 20 dB per decade corresponds to one pole, correct?
Okay, ma'am. If there are two poles there,
Then it would have been rather than if the slope would have been, let's say, minus 60 dB per decade. If the slope was minus 60 dB per decade over here, then you can see the slope change would have been minus 40 dB per decade, and which implies two poles. Like the same situation happened over here for zeros, right? We had two consecutive zeros, because of which the slope changed by plus 40 dB per decades. Is this clear?
yes.
Okay. So all of you, is this clear? Bode plots? See, frequency responses and Bode plots are very important when we are talking about circuits. A lot of information is drawn from these Bode plots only. That's why
Phase,
we need to understand them thoroughly. Yes, somebody is saying something.
phase plot.
Phase plot. Phase plot is not this straightforward. So for phase plot, what you need to do is you need to calculate the phases. Almost like how do you find the phase? So let's say if you have a transfer function of 100 s plus 10 s plus 100 s plus 1000, for example. Now if I want to write the phase of my transfer function, so how do I write the phase of transfer functions? First of all, 100. What is the phase introduced by 100? If it is positive, constant is positive, the phase introduced by it is 0 degrees. If it was negative, the phase would have been minus 180, right? Plus, numerator will introduce a phase of positive tan inverse omega by 10, and denominators will introduce a phase of minus tan inverse. So denominators introduce a negative phase, numerators introduce a positive phase. That is the convention. Okay. Now in this particular phase equation, basically what you will do is you'll start putting the values of omega, and with different omegas you will get the phases, and you will plot frequency phase, and you will start plotting the phases. This is somehow it will look like. Okay.
Okay, ma'am.
That is the idea. So generally for phase plot, we never go for approximate or Bode phase plots. There are definitely Bode phase plot, but it is not that common. Rather, for phase plots, we try to go for actual phase plots, at least at the poles and zeros. Like you can calculate the values at poles and zeros, right? They are very easy compared to other frequency values, and you try to extrapolate and you get the curve. And yeah, that's how you analyze. And let's say if this is my phase crossover, sorry, gain crossover frequency. So at my gain crossover frequency, whatever is the phase value, this particular phase is used in calculating the phase margin. 180 degree minus 5. Okay. And this relates to stability of the system, or circuit, whatever you say. Clear? Any doubts?
What is per
Ma'am,
octave?
Yes.
What is per octave?
Sorry.
Per octave? Octave per something होता है.
Octave per centimeter. Okay.
हाँ.
So, octave when we do, yeah, octave was, what was the unit? Can you repeat once again? It's octave per dB per octave, I guess, right? Mm, dB per octave was, it's also a unit used octave, yeah, decibels per octave. It is also the similar kind of denotion for slopes. So here the slopes we are denoting with dB per decade, where we are considering the decade as our frequencies, right?
Yes.
ma'am,
Yes.
ma'am, pole frequency means its slope is increasing or decaying. Can we decide it by name, sir?
Uh, Sorry, can you repeat once again?
Pole frequency means it will be decayed minus 20 and or not. Zero frequency will increase. We can relate that way or not.
So you should always relate to the difference in the earlier frequency versus new frequency. What is the slope change? If the slope change is positive, then how much was earlier and how much is the change? Depending on that, you can say whether there is a pole or a zero at that point.
When it was in denominator, then it will definitely will decay the slope. Is it true, ma'am?
Huh?
Actually, in transfer function, poles are in a denominator. Yes.
Yes.
So they will definitely decade in my 20 and
Yes, poles will generally decrease your slope and zeros will try to increase your slope. That is
yes,
obvious.
yes,
Yeah.
ma'am. Some,
So
but
you
in
can direct.
assignment, but in
Huh.
assignment three, in assignment three, they given graph of without slope. They that did not give mention any slope, but they
Hmm.
given for WP1, WP2, WP3.
Huh.
They asked to find out WP1 or something,
Hmm.
but they didn't mention. But slope was increasing, ma'am.
Slope is
Increasing order.
increasing.
Yes, ma'am.
It's
Increasing
an
order, ma'am.
increasing order, right? So if it
Yes,
is
ma'am.
increasing, most probably there is zero that is present, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
You can
Initially,
say.
the slope was starting from initially it was not from 0 dB or 60 dB. Straight, it
Huh.
was not 0 dB, ma'am. It was starting with some slope from origin and starting and increasing, ma'am. Oh, till WP3.
Sorry.
The slope was increasing from origin,
Huh.
ma'am.
Huh.
Uh, with some d with plus 20. It doesn't mention any slope, but it was increasing
Okay.
till WP3, ma'am. There are
Okay.
WP1, WP2, WP3. At
Okay.
WP3, the slope was 0 dB, ma'am.
Okay.
Yes, ma'am. So it means there are zeros or poles. I have some doubt.
So if it is increasing, then definitely that means there are zeros present. If
So
the values graph is increasing, it's going upward, that means there are zeros present. And if you see, okay, so there is something that I did not mention, maybe I'll mention here. So let's say from in all the examples till now, what we observed is our DC gain was straight line, right? Until we encountered a first pole or a zero. But what will happen if you have a pole at zero or a zero at zero? So your graph, what will happen is your graph will start increasing from here only with plus 20 dB per decade if you have 0 at s equal to 0. Okay? And your graph will start reducing from here itself with a slope of minus 20 dB per decade when you have pole at s equal to 0. Is this clear? So this also you have to keep in mind. Like basically the idea is that here the poles and zeros are at zero only. So your beginning of your graph only will start with either increasing or reducing slopes if you have poles and zeros at zero. Okay.
ma'am, definitely there will be some poles and zeros. But if we put s equals to that, then we get only DC gain only, ma'am.
No, if so, yeah, if you have like if so, how will your transfer function look like when you have a pole or a zero at zero? So your transfer function will look like somewhat this s plus 10, let's say, upon s plus 100, s plus 1000, right? And then now here in this case, if I put s equal to 0, what I get is my transfer function becomes 0,
Yes, ma'am.
right? So, and when your transfer function goes to 0, so how do you calculate your DC gain? Like, so this is the situation, right? Like, you cannot have a value. So, uh, what ideally is done in such cases is uh, you take S common from numerator as well as denominator. Okay. So mathematically this can be done, right? There is nothing wrong in this. Correct?
Yes, ma'am. Yes, ma'am.
You cancel both the s's and then now you substitute s equal to 0. So this becomes infinity, right? Oh, but here again, since this becomes overall, it will be 0. But that's still fine. Then basically, the only thing that it will change is that now your gain will be starting from 0 volt by volt because your DC gain is 0. But if you have a transfer function like this, let me say s plus 100. And yeah, s plus 1000. So anyways, the idea is you have to put s equal to 0. So in this case, when you put s equal to 0, so it will go to infinity. So decimal will go to infinity. But in these type of situations, your system will start from some specific DC gain and your slope will be increasing or reducing depending on that. But yeah, you can observe this kind of curves also, like where it is increasing from the beginning itself. So there is basically slope from the beginning itself. That behavior basically comes when you have a 0 at s equal to 0 and a pole at s equal to 0. 0. So that is the idea.
Ma'am,
Yes.
for first transfer function, the slope will increase plus 20 dB. It means example, ma'am. You give an example below.
Ha ha ha.
It
The
means
slope
at our
is,
slope will
yeah.
if
So
we put
here,
s square, then it will be minus 40 dB from origin onwards. It will increase minus 40 if s square.
yes, yes.
Yes, ma'am.
If it
Okay, ma'am.
is s square, then it will be plus 40 dB per decade. The slope, like in the
From
beginning
origin.
only, it will, yeah, from origin only, it will increase. That is
Okay.
not actually origin, it is low frequency, very low, because you cannot put a 0 over
Yes, ma'am.
here.
0.11,
Yeah,
0.00.
0.1, 0.001. You can go as low as possible, right? But it can never be 0. So you have to
Yes, ma'am.
reduce it by decades. So yeah, that is the only thing. So this never starts from 0. Your frequency axis will never start from 0, and you can never have a 0 frequency. You can have very small frequency approaching 0, but 0 frequency will not make sense because you are reducing it by decades, right? So every time you have a fraction, you can reduce it further by a decade. So 0 is never possible to come in this axis. That is the only idea. Okay. So hope Bode plots are clear, like how to plot them, how to extract information from them. We also did this example, right, where the plot was given and you had to write transfer function. So all these things are clear. Any doubts in the Bode plots? Is this clear to everyone?
Oh, ma'am.
Bode plots?
Yes, ma'am.
Okay. So with this, now let's start with today's problems, right? So it is given that a plant has an open loop transfer function of this. P is equal to 10 upon S plus 0.1, S plus 2, S plus 50. The approximate model obtained by retaining only one of the above poles, which is closest to the frequency response of the original transfer function at low frequency is. So you have to basically suggest a transfer function which is equivalent to this transfer function at low frequencies, right? So first thing that we'll do is find the DC gain, right? So you have to find the DC gain of given transfer function. So what is the transfer function's DC gain in our case? This is 1, right? Because we are looking at the low frequency approximate transfer function. So first of all, the transfer function should match. And if you look at the frequency values, the lowest frequency possible is with only single pole, right? Only one pole. So you will definitely use 0.1 as your dominant pole, right? So your transfer function will only have one pole, which is 0.1, S plus 0.1. Now, to maintain the DC gain, how much should be my value over here? What should be my constant A naught here? Yes, what will be the A naught? To maintain the DC gain? The A naught should be 0.1, right? If A naught is 0.1, then only you will get a DC gain of 1, right? Did you understand this? Any doubts? Is this clear? Have we approached this problem? Okay. So hope this is clear. If you have any doubts, please unmute yourself and ask. Okay. Okay. Moving on to the next problem. So in this problem, with a feedback path added to a system with a gain factor of alpha, what happens to the overall gain of the system, assuming large value of open loop gain A beta? So if open loop gain of a system is A into beta, then closed loop gain of the system will become A beta upon 1 plus alpha into A beta. Correct? Is this clear? So this is something very fundamental, right? We all know. Now it is given that A beta is much larger than 1. Like it's very large. So what I'll do is, since A beta is much larger, so 1 by A beta tends to 0. Correct? So the closed loop gain becomes 1 by alpha, right? Approximately 1 by alpha. So here it is basically asked that with this feedback being added, what happens to the overall gain of the system? It becomes controllable through 1 by alpha alone. It becomes controllable through A beta alone. It becomes controllable through alpha alone. It becomes independent of A beta. So if you observe, it becomes controllable through 1 by alpha is the most accurate one, right? So because the majority of your closed loop function is 1 by alpha. So the most accurate answer is it becomes controllable through 1 by alpha alone. Okay? It is definitely independent of A beta, but it's not um, like 1 by A beta is still a small value, right? It's not like it has cancelled out completely. That's not the case. So that's why we are not opting for option D. The most accurate option that can be selected is option A. Okay? So, yeah. Now moving on to the next question. So here, the transfer function of an amplifier is given. Transfer function is 1 plus s 5 into the power 6. Okay. Find its DC gain, upper 3 dB frequency, and gain bandwidth product. Okay. So first of all, what is the DC gain here? Yes, what is DC gain? For DC gain, what will you do? Put it s equal to 0. So when you put s equal to 0, you'll directly get 1000. Correct? Now,
Yes, ma'am.
it says upper 3 dB frequency. So we talked about that whenever you encounter a pole in 0, your gain either reduces by 3 dB if it is a pole, or it increases by 3 dB if it is a 0. Correct? But at what frequency that difference comes into picture? At what frequency you are checking that value? It's at either a pole or a 0 frequency, right? So when it is asked, what is the upper 3 dB frequency? So upper 3 dB frequency means basically you have to report the pole frequency only. What it is asking is pole frequency itself. So omega p is 5 10 to the power 6, which is 2 pi f. So if I want to calculate f, it is 5 into 10 to the power 5 hertz, or I can write it as 500 kilohertz, right? So you got DC gain, you got frequency. What is asked is gain bandwidth product. Gain bandwidth product is nothing but gain into pole frequency. So whatever is the gain, multiply with pole frequency, you'll get the gain bandwidth product. So here this is 1000 into 500 kilohertz. So basically this becomes 500 megahertz. This is gain bandwidth product. Okay. So the option A. Any doubts?
No, ma'am.
So let's move on to next problem. So first of all, do you understand what is being given? Like what is this diagram showing? Does anyone know what is this diagram?
MOSFET small signal analysis.
Yes, this is MOSFET small signal analysis. We call this a small signal model. So to give a brief, how we all understand a MOSFET by this, right? This is what we all understand our MOSFETs with, or we know that this is the symbol that we use for our MOSFETs, correct? But when we want to analyze this in our circuits, especially in analog circuits, we use an equivalent model of a MOSFET for the analysis. And how does that model look like? So the small signal model of MOSFET basically looks like this. This is source, this is gate, this is drain. Here you will have V out. This is plus minus VGS. And here you have a voltage controlled current source, that is VGS, GM VGS. Okay, this is basically this. इसका small signal model. Now after this, wherever you see your resistors, capacitors in your circuit, you can simply attach those resistors, capacitors into this small signal model of the MOSFET and analyze the circuit using the basic normal KCL and KVL. Okay, so this is the basic small signal model of our MOSFET. Now, here if you observe, so we have it is given that in the circuit V out is 2000 V2 minus V1. V naught is 2000 V2 minus V1. And what is actually V out? V out is actually whatever the current is flowing through this 2R resistor into 2R, right? So which is equal to I into 2R. R is already given 5 kilo. So I can write I into 10 kilo ohms. Okay. Now let's see that here there is this one current which is coming here GMV2 in this branch. This branch consumes a current of GMV1, right? And there is some current I that is flowing through this branch which is going through the resistor. So if I write KCL at this particular node X, so KCL at X, how it will look like? GMV2 is being distributed among GMV1 plus I, correct? So if I write I equal to GMV2 minus V1, I can write this, right? I equal to GMV2 minus V1.
Yes, ma'am.
Now if I substitute this I over here, I'll get GM V2 minus V1 into 10K equal to 2000 V2 minus V1. Correct? Now cancelling V2 minus V1 and dividing this 2000 by 10,000, what we will get? GM is 0.2 or GM is 200 milliamperes per volt, right? So here we have 200 milliamperes per volt. Is this clear to everyone? Any doubts in this? The only new thing here is the small signal model. For some people, it might be new. So, is this analysis clear to everyone? This was very simple, right? No complications at all. I hope this is clear. This problem is clear. Okay. Now moving on to the next problem. Again, it is asked that to use the same circuit. So let's use the same circuit. Okay. So in this circuit, it is said that GM is 100 milliampere per volt. It's given that GM is 100 milliampere per volt, and we already know that V naught is 2000 V2 minus V1. So we need to calculate the value of R. So we already wrote down, right? V2 minus V1 equal to I into 2R, where I is GM V2 minus V1 into 2R, correct? Yeah. Now we'll simply substitute 100 so R becomes 1000 by 100 into 1000 ohms. So this becomes R equal to 10 coulombs. Straightforward calculations, right? Now moving to the next problem. Okay, so in this particular problem, here uh, this is again the small signal model of the same MOSFET itself, but here the capacitors and biasing resistors have also been introduced. So basically, how this would look like. So this is this MOSFET with gate drain source. So the CGD capacitor is this CGD capacitor. This is CGS capacitor, and you have a load capacitor. So load is connected here with CL, and parallel to that you have RL, that is load resistance, and in gate you have gate resistor and a source resistor. From here you are giving input, and here you are taking V out. Here you must have applied VDD. Okay, so this is somewhat how your circuit must have been drawn. So this circuit's small signal equivalent will look like this. Okay, so in this question, for a given high frequency circuit, why high frequency? Because capacitors are in picture. Whenever we are considering low frequency, we know that Xc is 1 by omega c. Since the value of capacitor is always constant, which is whatever is given, it's there, but the reactance of the capacitance changes with frequencies. Now, when you have low frequencies, your Xc becomes very, very high, and we replace it with open circuits. Whereas when your this is when omega is low. Whereas when your omegas are high, your Xc is low, and you actually start seeing the behaviors. You start seeing the behaviors of these capacitors as they are in parallel, you can see, right? The resistors and capacitors are coming in parallel. So the whichever figure has smaller value, it's it is directly replicated in the results when you have parallel behavior. So that's why when you consider high frequency analysis at that time, analyzing capacitances or analyzing all the capacitors in the circuit is very important. So that's why this is a high frequency equivalent circuit with all the capacitors being introduced. Okay. So
Ma'am,
yes,
in low frequency,
yes,
we open circuit the capacitor.
yeah.
Okay, ma'am.
We consider that the impedance is very high, so it's almost like infinite impedance. So that basically means open circuit, right? So
Okay, ma'am.
in low frequencies, we consider it open circuit until anything is mentioned. If nothing is mentioned, we would consider it as open
Ma'am,
circuit.
in a low
Yes,
frequency, he was, in some questions there was given low frequency response. Then it
huh.
means they are not considered capacitors. They open the capacitors.
That is not always true. Why I'll tell you. Because when your capacitors are in parallel and you have open circuit behavior, then it is beneficial to you. But let's say your capacitor comes in series and you open circuit it over there, then the current path is broken, right? You will not have any current. So that behavior also depends on how your capacitors are connected, whether they are connected in parallel or in series. Because if they are connected in series, short circuited capacitors are beneficial to us. If they are connected in parallel, open circuited capacitors are beneficial to us in terms of uh, simplifying the analysis. Correct?
Yes, ma'am.
So that's very important to understand how the capacitors are actually connected in the circuit.
So
Okay.
we can select capacitor and remove the capacitance.
No, you
If we,
cannot do that. Like if you are using external capacitors, you can connect them in series or parallel as you want. But here, the capacitors that we are talking about, which are CGS, CGD, or CL, is an external capacitor, I could say. But still, like CGD, CGS, all these capacitors are internal capacitors, which are actually the effect that comes from the device itself. So these are not separate capacitors, so you cannot remove these capacitors. These are basically capacitive effects that come from the device. So these cannot be removed. They will stay intact. And you have to do your analysis around these capacitors only. Okay?
okay, ma'am.
Okay. All right. So for a given high frequency circuit, as shown below, with input signal V, having a resistance Rs, the values of circuit components are given, like Rg is 750K, Rs is 250K, C1 is 8 milliamperes per volt, RL is 10K, CG is 2 picofarad, CGD is zero point 0.6 picofarad, and CL is 25 picofarad. Okay. So find the midband gain and overall time constant of the circuit. Okay. We need to find the midband gain and overall time constant of the circuit. in this particular circuit for midband gain. Midband gain basically means it is a gain which is constant for a certain amount of time, which is not changing continuously with the frequencies. So let's say if I have this kind of response, then this is my mid-band gain. Okay. If I have this kind of response, this is my mid-band gain. So which is basically a constant gain for a certain amount of or certain amount of frequencies, and it's not continuously changing with frequencies. So what can we refer from this, right? So clearly one thing that we can refer here is that as my gain is not changing with the frequency, so definitely the capacitance effect is not prominent in my case, right? So to calculate these midband gains, what I can do is I can remove the capacitors and analyze the gain. So the resultant, how will that resultant circuit look like? So here it will be RG, this plus minus VGS. Here we have Vn, and then removing the capacitor, here we will have GVGS, RL, and V0, right? So what is V0? V0 actually is, if we observe that whatever is current flowing through this um, voltage dependent current source, whatever the current is flowing through this voltage dependent current source, if I change the direction of this current, so that means minus Gm VGS and into RL. So basically the drop across RL is my output voltage, right? So this drop across RL would be minus Gm VGS into RL. Now if I have to calculate VGS, I can calculate from here, which is V1 into Rg upon Rs plus Rg. So V1 is VGS. Oh, okay, so let it be this way only. So now substituting this in here, we'll get V out equal to minus Gm into RL into Rg upon Rs plus Rg. Gm into RL, Rg upon Rs plus Rg into Vn. Now gain is nothing but V0 by Vn. So which is basically minus Gm RL Rg upon Rs plus Rg, right? I can calculate my gain by substituting all the values which were already given. Minus Gm was 8 milliamperes per volt. Gm is 8 milliampere per volt. 10K. Rg is 750K by Rs plus Rg is 750K plus 250K. That is 1000K minus 8 milliampere per volt into 10K into 750K. by 1000K, 1000K and 10K. So here we are left with 100, and this K cancels with this milli, so this is minus 8 into 750 by 100. So what is the gain value that you're getting? Did somebody calculate the gain? How much is the gain? It's minus 60,
16, ma'am.
right?
16.
This is volt by volt. So this is what we have calculated as gain of the system right now. So one part is done, that is minus 60. Now there was another part, right? So you have to calculate the overall time constant of the circuit. So when we talk about time constant of the circuit, time constant, it is given by R into C. Time constant is given by R into C. Okay. So what we can do is overall time constant can be denoted as sum of individual time constants. Okay. So here we have three different capacitors, and when we have three different capacitors, corresponding to that, if we calculate the impedances, or I should say the resistances at or um, those nodes, will get the equivalent resistance at that particular node as well as the capacitance at that particular node. And when we multiply R into C, we get the time constant. So what are the capacitors that we have? We have CGS into, let's say, the equivalent capacitance is RGS plus CL into its equivalent capacitor is RL plus CGT into, let's say, RGD. Okay. So what is RGS? Like if you look from the gate side, what is the resistance that you observe for your circuit? Which is, it is actually equal to RS parallel to RG. Okay. And when we talk about RGD, it is actually a resistance being observed from in between the two ports. That is when you observe your resistance somewhat from here. Okay. This is the CGD. This is G, this is D, and this is S. So S is grounded. You have G on one side and S on other. And RGD basically means it is a resistance which is connecting your gate and drain. Gate and drain terminals or ports, you can say. Okay. So we give RGD as RL plus RG parallel RS plus GM RL into RG parallel RS. So this is the formula that is obtained when you calculate this RGD resistance, which is actually um, the resistance shared between two ports, we can say input and output ports. And CL into RL, it's straightforward, so we don't have to do anything. So now the idea is we need to calculate this RS parallel RG plus CL into RL plus CGD into this RGD total. So, um, first of all, can you quickly calculate RGS and let me know what is the value of RGS? So, RS is 250, 250K parallel 750K. So, can you people quickly calculate this RGS? What is the value that you are getting for RGS?
187.5.
187.5K,
Yes, ma'am.
right?
Yes, ma'am.
187.5. Okay. What about RGD? So RGD is basically 10K plus 187.5K plus 8 millions per volt into 10K into 187.5K. What is the value of RGD? Yes. How much is RGD?
151.97 mega ohms.
Okay, so how much is it? 151.97
97 mega
mega
ohms.
ohms. Mm, I guess
Is it correct, ma'am?
decimal place is a little off. It's 151, 15197.5
Yes,
kilo
ma'am. Yes,
ohms.
ma'am.
So
Yes,
that
ma'am.
means one decimal is
Sorry,
missing.
ma'am.
So,
Yes, ma'am.
yeah, can you
Yes, ma'am.
check
All.
once?
15 mega, ma'am. I think
Yes, yes, it's 15 mega.
15, ma'am.
So it's 15.197 mega ohms, right? So if this is RGD, now if I have to calculate the time constant, the overall time constant, then it is CGS. CGS was how much? 2 picofarad. So 2 picofarad into RS parallel RG, which is 187.5 kilo ohms plus CL, that is 25 picofarad into RL is 10K plus CGD is zero point 0.6 picofarad into RGD. This is 15.197 mega ohm. So how much is the time constant that you're getting?
9.74 micro.
Yes, 9.743 microseconds. Correct. So this is your option. Yes. Here the answer is in nanoseconds, but when you convert, you'll get it in micro. Okay. So let's quickly move on to the next problem. So again, for the same circuit, we have to find the upper 3 dB frequency gain bandwidth product. So when time constant is R into C, and we talked about this earlier also, pole is actually 1 upon RC, right? So whatever frequency that gives you the time constant, it actually comes from the dominant pole. So you can directly, like if tau is RC, so I can write my pole to be 1 by RC, just for simplification. And there is a complex method also, which is identifying the AC nodes and calculating poles at each AC node and then figuring out the dominant pole. But uh, uh, for the sake of this particular subject, uh, uh, we're going for the easier method. So considering that we have already calculated the time constant, and 1 by time constant is actually the pole. With this concept, we'll find the value of pole. So tau we have already found out it is 9.743 microseconds. Then the pole value would be just 1 by 9.743 microseconds. So how much is the pole value that you're getting? So if I tell you the value of pole, it is 102.632 kiloradians. Yeah, 102.632 kiloradians. This is the value of pole. Another question was to find the gain bandwidth product. So gain bandwidth product is basically nothing but pole value into gain. So gain we already calculated, it was 60 volt by volt. Mm, yes, gain was 60 and pole value is here, so it is 60 into 102.632 kiloradians. So gain bandwidth product will become, okay, so this is in radians. If you, okay, it is asked in kilohertz. So since it is asked in kilohertz, maybe we can convert this to frequency, that is 102.632 by 2 pi, which is 16.334 kilohertz. And I can directly write it in kilohertz over here. So this is 16.334 kilohertz. So the gain bandwidth product comes out to be 980.07 kilohertz. So for the given circuit, the gain bandwidth product is 980.07 kilohertz. Okay. Um, Again, the question is that for the same question, if we have to find the value of RL such that the 3 dB frequency becomes 20.166 kilohertz. So F is given 20.166 kilohertz. So here now we have to go backwards. So here F is given. From F we will find tau. Tau, from tau we will substitute the tau in this formula. And from here we will calculate the value of RL. So that is the process that needs to be followed. So from F you will first find omega, which is F into 2 pi. And this will give you tau. Okay. Then from tau, we will substitute it in the formula, that is tau equal to CL into RL plus CGS into RS parallel RG um, plus CGD into RGD. In this formula, we will substitute, and from there we will find the value of RL. So, what do you people want? Do you want me to calculate, or maybe I can give you the values? You people can try it at home, right?
Okay, ma'am.
Because it's a lengthier process, you have to go back iterating. So I'll directly give you the values for RL. RL is 8 kilo ohms. Okay. So this is the value of RL that you'll obtain. Just you have to follow the steps. So whatever we did in previous question, you have to backtrace it and you'll get this value. Okay. So this is option A. It is 8 kilo ohms. Now moving to the next problem. So this problem is related to Miller's theorem. So in Miller's theorem, the idea is whenever there is a component, a resistor, a capacitor, or any component, when it is shared between two ports, like input port and output port, two different ports, and a component is shared. So, like this is input, this is output port in a two-port system. Let's say I have this component which is shared between input and output. So, handling this component, it's very difficult. If you have, you can understand, right? When you have to apply KCL or KVL, but you have um, a node, a source that is shared between two nodes. There is no reference. So it's very difficult to analyze those points, right? So similarly, here also we face this issue. So Miller came up with this problem. We commonly know it as Miller theorem, where we say that, let's say if Z is here, okay, and Z needs to be shared. So Z will have two parts. One part will go into input and another part will go into output. Okay, and this value will actually depend on Zn, like the value of the component, into 1 minus A, that is the gain of the system. Okay. Similarly, Z out is also given by, oh, sorry. So here it was Z, right? Z into 1 minus 1 by A, 1 minus 1 by AV. Okay. So most of the time what happens is our gain AV is negative, because of which these convert to Z1 plus AV, and this converts to Z1 plus 1 by AV. Okay, this is basically because of the signs and conventions everything. Okay, so here, according to Miller's theorem, what is the impedance in the input and output port if I1 is 20 milliamperes and I2 is 40 milliamperes, with Z being 2 kilo ohms. So here This is I1, this is I2, same. So gain AI is I2 by I1, but uh, the direction of I2, and so basically I2 in output you look into the current flowing um, through your load, right? So because of which you will have a negative over here, and your gain will come out as AI equal to 40 by 20 milliamperes. So AI will be 2. This is amperes by amperes, okay? Oh, sorry, minus 2. And here you will simply substitute that. So Z is given to you as 2 kilo ohms. Now since Z is 2 kilo ohms, so Zn will become 2 kilo ohm 1 minus 2, which is 6 kilo ohms, and Z out becomes 2 kilo ohms into 1 minus 1 by 2 is 1.5. So Z out becomes 3 kilo ohms, and this is Zn. So you can clearly observe that when you have a shared, um, like when you have a component, be it a resistor or a capacitor, and it is shared between input and output ports, uh, the effect of that particular component on input is much higher compared to the output. You can clearly see, right? So it is almost the gain times. And as the gain values are much higher, so in the input side, the impedance increases by gain times compared to that in the output. And that's also a reason that these Miller components need to be analyzed very carefully, as they can change the whole behavior because their like uh, effective values in input and output are quite variable and significant also. Okay, so yeah, moving on to the next problem. Any doubts in this? No
Ma'am,
doubts, right? So,
ma'am,
yes.
in this Miller theorem, if type of amplifier is changes, then the formula will also change. Or
No, most of the times we go with gain only. So, and formula remains same. It's just that plus minus may sometimes there is a little this thing like plus and minus may whether to take plus or minus, but more or less it comes out to be same. To be even more precise and convenient, actually the gain values are always larger than 1, right? Whenever you have an amplifier, you always want your gain to be as high as possible, right? So like 120 dB, 60 dBs. 60 dBs is 1,000 times. 120 dBs, you can imagine. So it's basically um, like 6 times 10 to the power 6. So for such large values, 1 plus AV becomes AV, and 1 plus 1 by AV almost becomes 1. So in that case, your plus minus issue also goes away, but more or less the behavior remains similar.
but in some textbooks or I seen that Z in equals to Z into 1 by 1 minus CAV, and
Huh.
Z out equals to Z into AV by some simplification 1 by 1 minus 1 by AV.
Sorry, what
Z
was
in
that?
equals to Z into
Huh.
1 by 1 minus AV.
1 by 1 minus AV. Okay.
Z out equals to
Hmm.
Z into 1 by 1 minus 1 by AV. That AV
Okay.
goes up.
So if this is the situation, then let's say your AV is 1000. Okay. If
Yes, ma'am.
AV is 1000, distance to 0. So here your Z out will come as Z in, similar to this, right?
Yes, ma'am.
And if your AV is 1000, is it 1 upon 1 minus AV? I guess you must be missing something.
I think
It should
that
come out. So when you simplify it in input side, it will come out to be like gain times of that component, and in output side, it should come out to be only that component. And more or less, it comes out that way. So by simplification, uh, yeah, you can check, like you can cross check it. So if I simplify, Zn is Z times AV and Z out is Z for large AV. So this is the behavior that you always observe. Maybe you can cross check it once again. Okay? Yeah. So with this, let's move on. So this is the final problem for today. So in this problem, you have to apply the Miller's theorem to find the equivalent capacitance for the given nodes. Here, gain is minus of AV. So what will be Cin value? Cin is C into 1 minus AV. So okay, let's go. Maybe I'll write A. So there is no confusion. And C out is C into 1 minus 1 upon A. So this becomes C into 1 plus AV, and C out becomes C into 1 plus 1 by AV, right? So this is A option, correct?
yes, ma'am.
This is directly from the last problem. So yeah, these are the problems for today. So I'm done from my side. If you have any doubts, feel free to ask.
Ma'am,
Yes.
I have a question that in assignment 3, there was a question, ma'am. They
Okay.
are asking about low frequency response. They given a MOSFET with
Ah,
capacitors with CGD, CL or something, and
yes.
they asked about omega P3, but the response is like increasing order, ma'am.
Okay.
They given low frequency response. I didn't understand how to get low frequency response. Can you explain?
I mean, I have not seen the problems for week 3, so I cannot comment on that. But basically, low frequency response means lower frequencies you have to observe.
Okay, ma'am.
So most probably omega P3, is it like closer to y-axis? Is that the pole? Omega P3?
No, ma'am. It's away from the pole,
Oh, it is away from
the y-axis.
the y-axis. But basically, you have to find the value of omega P3,
Yes,
right?
ma'am. Yes, ma'am.
But some values must have been given, right? Y-axis must have been given to you, right?
No, ma'am. They given a x-axis and given a MOSFET, ma'am. MOSFET, we can find voltage gain from that transfer
Hmm.
function, so that we can find the whole frequencies. I think.
Yeah, so so you need to solve that. Uh, so basically, this analysis needs to be done.
Yes, ma'am. Okay, ma'am. I understand that,
Yes,
ma'am. But I have a doubt that why the whole frequency was increasing,
pole frequency was increasing.
increasing order, ma'am. The graph was low frequency response is in increasing order, not in
So
decreasing
if
order.
if if it is increasing in order, that means there are more zeros in the system compared to poles. That is the inference that you can
Okay,
get.
okay,
Yeah.
ma'am.
But unless you solve the transfer function, you will not understand like where the zeros are coming from and what are their values and everything. So
Okay,
for that, basically, transfer function needs to be solved.
yes, ma'am.
Yeah.
Just move it.
Any other doubts? Okay, so if you people don't have any doubts, maybe we can break over here and meet again next week with new set of concepts and problems. So that's all for today. Thank you everyone for joining. Have a wonderful evening ahead. See you all next week. Bye.
Bye.